Lecture 19. From General Relativity to Spacetime.
Last lecture, we explored Einstein's theory of special relativity. We saw that it was motivated by Einstein's desire to avoid a specific metaphysical position about the nature of reality, the substantival view, which suggests that space itself is a substance. In an effort to combat this view, Einstein suggested that how fast one would observe the speed of light to be is not relative to how fast one is moving in comparison to space itself. There is no such thing as space itself, he believed, and so the speed of light is not relative to how fast one is traveling. The speed of light is constant in all reference frames. We saw that important metaphysical consequences followed from this, that simultaneity, length, and even how fast time passes are relative to reference frames. But I also mentioned that Einstein's theory of relativity, specifically his theory of general relativity, seems to commit one to a substantival view of what Einstein called spacetime. So Einstein's theory may have committed him to the very kind of thing that he wanted to avoid. But must relativity be interpreted this way? To answer this question, we first need to understand general relativity. In special relativity, we saw that all laws of physics, including the speed of light, are constant in all inertial reference frames. However, an inertial reference frame is one that is not accelerating, decelerating, or changing direction. So what about those? Are the laws of physics constant in non-inertial reference frames too? If they are not, Einstein's case against the substantival view is weakened. If the laws of physics are different in non-inertial reference frames, it could be because those frames are accelerating in relation to space itself. So general relativity is Einstein's attempt to explain how the laws of physics, including the speed of light, are constant in all reference frames, including non-inertial ones. At first, it seems that the laws of physics are different in non-inertial reference frames. Consider when you're in an airplane that's taking off, that's accelerating. You feel like you are being pushed backwards. If you were to put a marble in the middle of the aisle, it wouldn't just sit there, but would roll toward the back of the plane. After decelerating upon landing, it would roll to the front. Sharp turns would cause it to go to one side or the other. This would not happen if your speed was constant, and so it seems in non-inertial reference frames, the laws of physics go out the window. Contrary to Newton's first law of motion, things don't remain at rest in non-inertial reference frames, they fly all over the place. But when you think about it, however, this is not that unusual. This kind of discrepancy can be found in inertial reference frames too. Suppose you were traveling in a non-accelerating spaceship. In that inertial reference frame, you let go of the marble in midair, and it would just float there. But do that while you're standing in your living room, and the marble will fall to the floor. Have the laws of physics been broken? No. Gravity produced by the mass of the Earth accounts for this motion. We even have laws of physics that describe its effect. Einstein suggested that the effects of acceleration could be described and accounted for by exactly the same laws. In short, the effects of acceleration are indistinguishable from the effects of gravity and vice versa. In effect, you can mimic the effects of gravity with acceleration, and you can mimic the effects of acceleration with gravity. If so, the laws of physics are constant in all reference frames, not just inertial ones. It turns out Einstein was right. It was once assumed that heavier objects would fall faster than lighter objects. A rock twice as size as another rock would fall twice as fast, right? But this is not the case. Two rocks of any size will fall at the same rate. In fact, as they fall, their descent accelerates at a rate of roughly 9.8 meters per second per second. Notice that this means that you can mimic the effects of gravity with a spaceship that accelerates at 9.8 meters per second per second. In that spaceship, if you were to let go of two equally sized rocks, they would hit the back of the spaceship at the same time, just like they would land on the Earth at exactly the same time. Gravity mimics the effects of acceleration, and acceleration mimics the effects of gravity. 3 very important things follow from the equivalence of the effects of acceleration and gravity. First, we can finally explain Newton's spinning bucket. Anything that spins is in a non-inertial reference frame, so the spinning of the bucket mimics the effects of gravity. The water in the bucket is behaving as if a giant massive object surrounded the bucket, as if gravity were pulling the water towards the edge of the bucket. More importantly, this allowed Einstein's theory to be successfully confirmed during a solar eclipse by confirming what the theory entailed, that light bends around massive objects. Now, how did Einstein figure this out? Well, if acceleration and gravity are indistinguishable, then we can figure out how gravity affects light by figuring out how acceleration affects light. So again, let's say there is a spaceship, but it's sitting still on the Earth. You are standing outside the spaceship, shining a flashlight straight toward a window on the side of the spaceship. Obviously, the beam of light would hit the wall opposite the window. Now let's say you're floating in a hot air balloon, way up in the air, and the ship is moving upward at a constant speed in relation to you. As it passes you, you shine your light at the window. Since the ship is moving in relation to the light beam, the light would hit a spot on the opposite wall inside the ship just below the level of the window. When the light hits the window, the rocket is in a certain place, but by the time the light travels all the way to the opposite wall, the rocket will have traveled up a bit, and so the light will hit the opposite wall in a slightly lower spot. How far below would depend on how fast the rocket is traveling. But if you were to track the path of the light, it would be straight. Looking at it from inside the rocket, it would be at an angle from the window down to the opposite wall, but it would be straight because the rocket is traveling at a constant rate. But if the ship was accelerating, the path the light took would be curved instead of straight and angled. Let's say the ship was doubling in speed every nanosecond. If the light moved down 1 inch in the first nanosecond, it would move down 2 inches in the next, and then 4 inches in the next, 8 in the next, etc. Plot that path from inside the ship, and it's clearly a curved line. How much curve it has would depend on how much you are accelerating. Since the effects of acceleration are identical to the effects of gravity, light should curve towards a massive object that produces massive gravity. Now, the amount of acceleration needed to mimic the force of gravity on the Earth does not bend light very much, and so neither does the Earth. However, the Sun is a much more massive object, its gravity is much stronger, and thus it should bend light rays significantly. So, when Einstein was trying to prove his theory, the best opportunity to do so was presented by the Sun, specifically by a solar eclipse. To test his theory, an eclipse was predicted, and a star was found that would be behind the Sun during the eclipse but close to its edge. Newton's laws, which suggested that light rays travel in straight lines, predicted that you would not be able to see the star. Einstein predicted that the light from the star would bend around the Sun and still be visible. And then Einstein was right. The star was visible. The effect is now called the gravitational lens effect, and you can find really cool animations of it online. Third, we can also derive the effects of acceleration on the passage of time. Suppose in your spaceship you have 2 clocks, one at the front and one at the back. They are both programmed to indicate the speed at which they are turning by emitting a certain frequency of light, roughly a certain number of photons for every time their second hand ticks ahead by 1 second. Let's say 10 photons, one at a time for every tick. So suppose the clock at the back of the ship emits 10 photons as it ticks once. It emits those photons toward you at the front of the ship. But since the ship is accelerating, by the time they get to you, the ship will be going faster than it was when the photons were emitted. As a result, it will take longer for all the photons to reach you. If your ship is going twice as fast by the time those photons reach you, it will take twice as long for you to register those 10 photons. While your clock ticks over once and emits 10 photons of its own, you will only register 5 photons coming from the clock at the back of the ship. Since the speed of the light emitted by the clock cannot be slowing down, the clock at the back of the ship must be moving more slowly. It takes the clock at the back longer compared to your clock to emit 10 photons and tick once. And since, by the time the light emitted from your clock at the front reaches the clock in the back of the ship will once again be going twice as fast, it will actually receive those 10 photons twice as fast. While the back clock ticks once and emits 10 photons, it will receive 20 photons from the clock at the front of the ship. And so a person measuring the photons in the back of the ship would conclude that the clock at the front of the ship is moving faster. If you're having trouble figuring out why, think of it in terms of waves in a lake. Let's say there's a boat bobbing out in the middle of a lake, creating waves that emanate out from the boat. Let's say it's producing 1 wave per second. If you are swimming towards the boat, you will hit more than 1 wave per second. Let's say 2 waves per second. If you are moving towards the wave source, the frequency of waves you experience increases. If you are swimming away from the boat, you will experience fewer waves per second. Moving away from the wave source decreases the frequency of waves you experience. Now think of the light emitted by the back clock as a wave. Again, we'll talk more about the wave-particle duality of light later. The clock at the front of the ship is accelerating away from the source of the back clock's wave, and so the frequency of that wave will decrease. But the clock at the back of the ship is accelerating towards the clock at the front, and so the frequency of the wave it measures will increase. And since the frequency of light it emits determines how fast the clock is ticking, we must conclude that the front clock is moving more quickly than the back clock. So the acceleration of the ship causes time to pass more quickly at the front of the ship than at the back. But remember, the effects of acceleration are identical to the effects of gravity. Accelerating pulls your body backwards, just like placing a massive object behind you would pull your body backwards. So it must be that if there are massive objects behind you, or underneath you, time passes more quickly the further away you are from that object. So, let's say you put a clock on the ground floor of the Empire State Building and then one on the top floor, further away from the source of gravity, the Earth. The clock on the top floor should move faster than the one on the bottom floor. And it does. Such experiments have been done. The effect is even more pronounced if we put a clock in a satellite orbiting the Earth 20 miles up. In fact, the clocks inside satellites have to undergo periodic adjustment to keep them in sync with the clocks on the surface of the Earth. A GPS satellite can't tell your GPS device the appropriate arrival time if it's running ahead of yours. With both time dilation and gravitational lensing in mind, we can now understand what Einstein is talking about when he talks about spacetime, and what it means for spacetime to be curved. Take light, for example. The speed of light is constant and nothing can travel faster than it. As a result, the path that light takes between 2 points must, by definition, be the shortest path between those 2 points. If there were a shorter path, something else could travel there faster in violation of the nothing faster than light principle. And the shortest path between 2 points is also by definition a straight line. And so light must always travel in a straight line through space. However, we have already seen that light curves around massive objects, like the sun. So how can it be that light always travels in a straight line, and yet also curves around massive objects? The answer is that space itself, in which the line exists, must be curved. Think about a flat piece of paper with 2 dots on it. The shortest path between the 2 dots is represented by a straight line. Take a pen and draw that line. Now, curve the paper into a cylinder. Even though the actual distance between the 2 dots might be reduced, since you can only draw a line on the paper, the most direct way to get from point to point by drawing a line is still represented by the line on the paper. Now, just like you can only draw lines on paper, light can only travel in space. If the space is curved, the light will curve with it, but it will still be traveling in the most direct route in space to get from where it came from to where it is going. So it's not really the light that is bending, it's the space in which the light is traveling that is bending. We can say something similar about the effect of gravity on time. Think about the standard 3 dimensions that we encounter every day. Take a single mathematical point that has no dimensions. Now, stack up a whole collection of those points. You get a line. A line has 1 dimension, length. Extend that line by stacking up a bunch of lines together outside that dimension, and you get a square. The square has both length and width. Extend the square into the 3rd dimension to get a cube that has length and width and height. These are the standard 3 dimensions in which we move. But we also move in time. Stack a bunch of 3-dimensional objects, like a cube, into another dimension, and you would have a 4-dimensional object, one extended through time. Recall, when we talked about David Lewis's theory of persons, he thought of persons in this way. as four-dimensional objects spread through time. We can only experience one slice of a four-dimensional object at a time, but over time we could experience the entire object. The fact that clocks further away from a gravitational source tick faster than those closer to the gravitational source seems to indicate that the clocks that are further away from the gravitational source are traveling further through time. In the same way that a car going 60 miles an hour traverses a further distance than one going 30 miles an hour, a clock further away from a gravitational source seems to traverse more time. And so it seems that gravity not only warps space, but also warps time. And we would say the same for acceleration, since its effects are equivalent. And this seems to suggest that time is a substance, something that can be warped and traversed, something that collects more densely around the source of gravity, making it thicker and harder to traverse. It seems to suggest that it is more spread out and thin, further away from the source of gravity, making it easier to traverse. It is something in which an accelerating rocket travels, and that acceleration seems to warp and manipulate. But since the effects of massive objects and acceleration affect both the nature of space and time in a similar way, Einstein spoke as if space and time were interrelated. In fact, he spoke as if they were one entity on which gravity and acceleration seem to have an effect. For example, gravity, we might say, warps space-time, causing both light to curve around massive objects and clocks further from gravitational sources to move more quickly. But this is not an entirely accurate explanation. Einstein's general theory of relativity did away with the need to hypothesize the existence of gravity at all. The Earth orbits the Sun not because gravity holds it in place, but because the mass of the Sun curves the space-time around it, the space-time in which the Earth travels. If the Sun was not there, space-time would be flat and the Earth would continue on in a straight line. But thanks to the Sun, the space-time in which that line exists is curved, and so we keep going in circles. And when we jump, we fall back to Earth, not because gravity pulls us down, but because the mass of the Earth curves space-time in such a way that any trajectory through space-time that we could traverse under our own power by jumping inevitably curves back down towards the Earth. To traverse a space-time trajectory that doesn't turn back towards the Earth, we would have to expend enormous energy. We'd need a rocket. Minkowski diagrams, which I mentioned last lecture, are probably the best way to understand why Einstein's relativity dispenses with space and time as separate entities. They treat an object's location in space and time as a single point, and treat space-time as a substance through which objects travel. And if we conceive of space-time as a substantival entity, we once again have objective truths. Whether two events are simultaneous is relative to reference frames, but there is an absolute fact about their location and how they are related in space-time. The fact that hypothesizing space-time as a single entity has such grandiose explanatory power is reason to think that the hypothesis is true. A hypothesis's scope, its explanatory power, is a major boon for any scientific theory. And although the theory is not simple, because it introduces an extra entity, space-time, it seems to have all the other criteria a scientific hypothesis needs. It makes predictions, it gets those predictions right, and it coheres with what we already know. And so it seems that if we accept Einstein's general theory of relativity, we're accepting a substantival view of space-time. Now the listener may be confused at this point. You may be thinking, I thought you said Einstein was motivated to develop relativity to avoid being committed to a substantival view. But now you're telling me the theory he developed commits us to viewing space-time as a substance? What's the deal? That's a great question. You're clearly paying attention. Here's the thing. Einstein didn't think relativity necessarily committed one to viewing space-time as a substance. To understand why, we're going to have to dive into some philosophy of science. Now that we understand relativity, it's time to do some hardcore metaphysics and explore the nature of reality. Does space-time really exist? There are two views in the philosophy of science about how to understand and interpret scientific theories, especially those with hypothetical entities that cannot be directly observed. There's realism, and then there's instrumentalism. Consider atomic theory, which suggested that all matter consists of tiny particles called atoms that are combined and configured in different ways. The atoms hypothesized were made up of protons and neutrons in a nucleus and electrons orbiting around that nucleus. Atoms combined by sharing electrons to form molecules. When this theory was first proposed, there was no way to directly observe the existence of atoms. It just hypothesized their existence and how they behave and combine. But the hypothesis produced really accurate predictions. By hypothesizing their existence and structure and how they would share electrons, one could predict the outcome of a chemical reaction. It could also be used to explain the weight of substances or why material behaved as it did. It was a very powerful theory. There are two possibilities here. One is that atoms exist as hypothesized, and the reason for the accurate results is because they behave as the theory suggests. This is the realist view. Another possibility is that the hypothesis merely produces accurate predictions, but does not actually describe the way the world is. Atoms don't actually exist, but hypothesizing that they do is a useful tool, an instrument for making predictions. This is the instrumentalist view. We have since observed atoms directly with electron microscopes, but similar questions can now be raised about the existence of subatomic particles like electrons, protons, and neutrons. We can observe their supposed effects, but we cannot observe them directly. And we could say the same thing about the particles that supposedly make them up, like quarks. We could certainly say this about the Higgs boson, better known as the God particle, which was supposedly discovered by the Large Hadron Collider. We observe their supposed effects, but we don't observe them. Now, I personally believe in the existence of electrons, protons, quarks, and the Higgs boson. I'm not an instrumentalist about such things. But instrumentalism is sometimes right. Sometimes an hypothesis is useful, but does not actually describe reality. One very useful hypothesis that may not describe reality is the theory of gravity. Newton hypothesized its existence, and that assumption was very useful for describing planetary motion and how objects behave on the Earth. But, as we have seen, if Einstein is right, gravity doesn't exist. It's just an apparent force. Einstein seemed to favor an instrumentalist view of spacetime. Hypothesizing the existence of spacetime and speaking as if it actually exists is a very useful way of making predictions about how light and objects behave. But we need not think it accurately describes the way the world is, that spacetime actually exists as a substance. Ultimately, it could be that the curvature of spacetime isn't an intrinsic property of a substance, but just a way of expressing the way that objects in the universe relate to one another. Light bends around the sun, not because spacetime is curved, but simply because that is how light relates to the sun. Although we can actually observe atoms, we will likely never be able to observe spacetime. While there may someday be a way to settle the issue, there are currently good reasons on both sides that keep this issue up in the air. One reason for favoring the substantival view is the fact that to solve equations about how massive objects curve the spacetime they are in, you have to assume that spacetime is flat at infinity, that infinitely far away from the massive object, spacetime is flat. The equations don't work if you assume that spacetime has no properties at an infinite distance, that its curvature is indeterminate, but it's only possible for spacetime to be flat if it is a substance. It can't be flat if it doesn't exist. So the math seems to favor the substantival view. Additionally, the general theory of relativity seems to entail that spacetime has properties even when there are no objects around, and thus there are no relations between objects. If the relational view is right, the properties of spacetime are just properties of the relationships between objects. So if there are no objects and thus no relations between objects, then spacetime would have no properties. But as the equations show us, if there are no objects around, it seems that spacetime has no curvature. It's flat. And again, it's only possible for spacetime to be flat if spacetime is a substance. On the flip side, however, there are some things the substantival view cannot account for. Einstein proposed the hole argument, where he imagined a hole of empty space surrounded by clumps of matter. The problem is, as Einstein describes that surrounding matter, the properties of the spacetime in the hole, how it would be curved by the surrounding matter, is indeterminate. In other words, when you do the math and crunch the numbers, you realize that there is not one single answer for what properties the spacetime in the hole has. there are multiple ways to describe how that spacetime is curved that are completely consistent with how the surrounding matter is arranged. But if spacetime is a substance, it cannot be curved multiple ways. There must be only one right answer, one and only one way that the space in the whole is curved. This is a problem. Not only does the substantival view leave such questions unanswered, but it has no way to explain why the spacetime in such a whole would be curved in one way rather than another. But the relational model has no problem dealing with the whole argument. In the same way that it can maintain that when no matter is present, the curvature of spacetime is indeterminate, it can suggest that when there are multiple ways that spacetime could be curved, how it is curved is indeterminate. The relational model is also simpler in a scientific sense because it has to assume less. It hypothesizes fewer entities. It does not treat spacetime as a substance. On the other hand, however, the substantival view seems to have very wide scope, strong explanatory power. And that's a huge mark in its favor. And so which view you favor depends on your metaphysical leanings. Is it okay to assume that something exists because hypothesizing that it does has explanatory power? Or do you prefer simplicity? But regardless of whether you accept the relational or the substantival view, relativity still entails the temporal ontology that we talked about a few lectures ago, one that is incompatible with free will. Recall that simultaneity is relative to reference frames. Two events that are simultaneous in one reference frame will not be simultaneous in another. Now, let's say that you're in a reference frame where events A and B are not causally related and are also not simultaneous. A occurs before B, let's say. Now, as A occurs, you would have to say that event A exists, and it exists along with you. You and event A coexist because you exist simultaneously with it in your reference frame. But there is another reference frame in which A and B occur simultaneously, and thus in that reference frame, A and B coexist. But existence is not something that is relative to reference frame. If you coexist with A, but A coexists with B, then you must coexist with B, even though event B lies in the future of your reference frame. But it's also true that there is some other future event C that is simultaneous with B in some other reference frame, and thus coexists with B, even if it isn't simultaneous with A in any reference frame. And since A coexists with B and B coexists with C, then A must coexist with C, even though it's impossible for A and C to be simultaneous. Thus, what relativity does is produce a picture of the universe that shows it to be a giant four-dimensional block, a collection of objects and events spread out through spacetime that bear certain relations to one another. You can think of those objects and events as being situated in spacetime, like the substantival view would suggest, or you can simply think of them as bearing spacetime relations to one another. Regardless, relativity suggests that all the objects and events in the entire history of the universe coexist in a giant spacetime block. If there was a privileged reference frame that accurately described when objects came into existence and events occurred, we would not be committed to this view. But there is no such reference frame according to relativity, and so we are committed to the block world view, omnitemporalism, which suggests that the future exists before it occurs. As we've discussed before, this view of time is incompatible with human free will, at least the libertarian variety, because it entails that we can perform no actions other than the actions which exist in the block. But if the whole of spacetime exists as one solid entity, is it possible to travel in time the same way that one travels in space? Does relativity entail that time travel is possible? Indeed it does, at least in some respects. And it is to those metaphysical questions that we will turn next lecture.